Hi everyone and welcome to this my video on estimating probabilities. My name's Darren from Maths Guru and hopefully you are going to love this video. Now behind me are the learning objectives which can all be downloaded from my little corner of the internet, mathsguru.com. Absolutely free to sign up. Head over there. It's got downloadable lesson notes, it's got the videos, it's got VCAA questions and so much more. Now, if you're watching this, you may be like, well, hold on a moment. This is part of the Mathematical Methods Units 1 and 2 course in Australia. Yes, but it's probability. And probability is universal. And so fingers crossed, wherever you are in the world, this video could be useful to you. But what are my learning objectives? Understand what the subjective probability is. Understand how we might be able to collect probability from data. Know what it means to be a relative frequency. Know how to find probabilities, know what simulation is and when we might use it, and find probabilities from areas. Sounds like a lot. Yes, it does, but actually this video is going to be pretty short. Now in the last video, you've watched the last video, yes? No? Well, again, it's on mathsguru.com and it was really good, yeah? We looked at the basics of probability, and yes, to be fair, we've done a lot of that in year 7, 8, 9, 10. And we're doing it again now, but methods tries to trip you up. It tricks you with a notation. So now notation becomes really important. And we sort of try to mix a lot of subject areas together. While this is the basics, at the end of the course, it does get a lot harder. And particularly in mathematical methods, units 3 and 4, it gets even harder still. So having a good foundation is really important. So don't skip the video. If you're sitting there going, what's he talking about? Then trust me, I don't know either. No, I'm joking. I do know. Right. I have to say, since I thought, as you can probably tell, my accent is British. Yes. Although I live in Australia and I have done for many years, I can't quite understand how it is that the United Kingdom and Australia are so excited about the weather. No, seriously. Everywhere you go in the United Kingdom, we talk about the weather. I come over here, and other than the fact that they call their weather service BOM, which I'm not going to say out loud for fear that, the FBI stormed the building. Yeah, I know, makes no sense really. Guarantee that people are there going, oh no, I've seen the radar. The radar says it's going to rain in 4 minutes and 33 seconds. No, look, it's the radar. I'm like, you what? Well, there you go. So when I look at this, I'm looking at this, and I'm doing it myself now. I'm like, oh, it's 50% chance of rain. What do you mean it's 50% chance of rain? How do they know? Where did that 50% come from? Is it there's a 50% chance? Does it mean that there's 50% that, at some point it's going to rain? Is it going to rain for 50% of the day? Is it if I look outside the window, there's going to be a round cloud with a 50% under it? I don't quite know. But to me, that is a subjective probability. Yes, it's a probability because I have no idea. It's not based on fact. There is no way anybody in this country can look out of their window or do computer simulations or whatever and know for a fact it's 50%. They may well have taken it from data and modeling or what have you, but again, I'm fairly sure that that's a subjective probability, and it's important as part of this course to understand what that actually is. Now, obviously, we get back onto a little bit more of terra firma when we estimate probabilities. And what does that mean? Probabilities from data. Yes. Now, data is king, isn't it? We believe all the data that's out there. No, I really wouldn't if I were you, because data can be manipulated, as can human beings. But, that's stories for another day. We can get data from experiments. I'm going to talk about one particular experiment in a moment, but we can record the data and then use that to find relative frequencies. Now, again, a relative frequency of an event happening is given by the number of times that event A occurs divided by the number of trials. Now, for example, if I was to toss a coin just once, yes, and it's probably a pretty bad example. If I was to toss a coin just once and try to find out the probability of me getting a tail, well, if it actually ends up as a head, then theoretically speaking, my probability would be 0. Yes? What about if I was to throw it again and get another tail? Well, it's still 0. And so we could keep going on. But, we actually know from all the stuff that we've done and probably all the trials we've done, the probability of getting a head or a tail on a coin is about half. We'll come back to that in a moment. So relative frequency is given by the number of times event A occurs divided by the number of trials. Now, not everything we can do in life actually has an experiment, and I learned that really quickly in the United Kingdom when I gave a group of boys, a group of 13-year-old boys, a load of thumbtacks, and as we call them in the United Kingdom, drawing pins. You know what I'm talking about? Those very sharp, pointy things that have the circle. Now, me being a young and impressionable teacher, believing the very best in everybody, I didn't see the problem in any of this because the general idea was you were supposed to take the thumbtack and drop it 100 times from the same height onto the same surface, and all you needed to do was work out, or all they needed to do was work out whether it landed thumbtack up or thumbtack on its side, because basically there is fairly little point that thumbtack is going to land straight on the point and stay that way, unless you're putting it in really hard with your thumb, but that wasn't the point of the experiment. So there were two outcomes, and what we're trying to do is try and work out, well, what is the probability of it landing thumb up? Of course, I didn't really think too much about this until I heard a chorus of, "Ow, sir, he just, ow, sir, he just stabbed me." And then, of course, boys put them under each other's butts, and then it was chaos after that. Now, having dispensed with that, never done an experiment again in my school career, Cambridge has very, very kindly not only allowed me to use their examples, but this particular graph. And what we find is that when I drop my thumbtack 10 times, I ended up with 9 of them actually as point up. All right, or thumbs up, or whatever else you want to call it. Now, when we had that would have given me a relative frequency of 9 on 10, which is 0.9. All right, so again, going back to that formula, I had 9 successes out of 10 throws, and so I had a relative frequency of 0.9. Well, guess what I did then? Well, the idea was you then did another 10 throws. So now you had a total number of trials of 20, and you worked out how many were thumbtack up. And what we noticed here was, let's say that was 0.855, and then it went down a bit. And every 10 trials, we just counted the thumbs up. Now, this is actually pretty beautiful. When my boys used to do it, we used to get something that looked a little bit more like this, that got closer and closer to, yes, this dotted line here. Now, what on earth is that dotted line there? Well, that's going to be the probability of the thumbtack landing up, because the more results we have, the closer and closer this is going to get. My relative frequencies get higher and higher, and we look like we're getting closer and closer to an actual probability. And that's where it comes here with something called a large number of trials. The bigger the number of trials, the closer we are going to get to the actual probability of an event. So I can't just toss a coin once. I could probably toss a coin 100 times, 1,000 times, 1,000,000 times. And I could keep doing this, and hopefully we would find that my relative frequencies will get closer and closer to the actual probability. And in that situation, probably for a coin of about 0.5. Again, probability of A, he says doing that, is given by the number of times event A occurs divided by the number of trials. So here's a beautiful example that will now test whether you've understood what I was talking about, or in fact even listening. But before I go on, can you do me a massive favor? I reached 10,000 subscribers this week. It's taken me 10 years to do it, and that's because nobody watches maths videos. If you can subscribe to my Maths Guru YouTube channel, it means the absolute world to me. It seriously does. It also shows me that people are watching and I'm not sitting here talking to myself. Just click that button. If you don't want to hear from me again, turn off notifications, but I would love you to hear from me again, and just keep supporting my channel. And more importantly, if you can actually tell your teachers and your friends and go, do you know what, actually there's a pretty entertaining British guy delivering some kick butt mathematics, I'd be really, really happy. And if you're in the UK, you can do it as well. Right. In order to investigate the probability that a drawing pin lands point up, Katia decides to toss it 50 times. That might be important. Now, obviously, good exam technique is to highlight, apparently, and to count the number of favourable outcomes, which turns out to be 33. Mickey repeats the experiment, but she tosses the same drawing pin 100 times and counts 62 favourable outcomes. Part A. We like Part A. What is Katia's estimate of the probability of the drawing pin landing point up? So here we go. A. What is the probability? The probability of, and let's say Katia is given by, well, how many did she got? She got 33 on 55. That's 66 on 100. Why do we like the 100 underneath? Because that's a nice easy conversion, which gives me 66%. Alternatively, we could write that as 0.66. Both of those are probabilities. It depends on what the question is looking for as to which one you're going to use. Right, what is Mickey's estimate? Part B. The probability for Mickey is going to be given by, what does she have? 62 on 100, which is going to be 0.62 or 62%. Oh, which of these is the preferred estimate of the probability from the experiment? And again, this strikes the very heart of your understanding. Probabilities get closer and closer to fact the more trials you do. So which one did the most trials? That would be Mickey. Which of these is the preferred estimate of the probability? I would actually say for part C, it would be Mickey. All right, because she did more trials. Now, part D is a bit of a trick. Based on the information available, what would be the preferred estimate of the probability? And I bet millions of you, or at least the 6 who are watching this, will turn around and go, oh, it's going to be Katya. It's going to be Katya. No, it's not. It's going to be Mickey. It's going to be Mickey. They did more, yeah? It's actually neither of them. Why? Because we need to keep having the maximum number of trials. So what we actually do for this question is say, well, Katya did 33. Sorry, try that one again. Katya did 55. And Mickey did 100 trials. So actually, if we combine their results, there was, in fact, 155 trials. See what I'm doing here? Katya had 33 successes. Mickey had 62 successes. Add those together, it gives me 95. And what does that become? Well, obviously, in this situation, I would fire up my CAS calculator and I would type into it, he says, ignoring all the rest of the stuff that's on there. 95 divided by 155 gives me 0.62. So 0.62, correct to 2 decimal places. And there we go. So in that situation, he says, turning off our computer or the calculator so we can see it. There we go. That would be a far better estimate because we are going to add all of my individual experiments together and get closer and closer, hopefully, to the actual probability. Now, simulation, again, story from my childhood. I used to love a program called The Sims, or SimCity, actually. And believe it or not, I managed to find an actual screenshot of SimCity. And the whole idea, and you may already know this, was you just built a city. I mean, okay, it was a simulation. I sat on the computer like a bit of a loner and just tried to build this city. The problem was I was really, really bad at this. I could never really work out how to get the water or enough water from the dam or the reservoir or whatever else I was building to all the businesses, and they would die. And as I say here, there were deaths. There were lots and lots of deaths. People repeatedly died. And in the end, I was just like, nah, I'm going to go into teaching. It's way less stressful and a lot less dependent on water. Right now, obviously, simulation is great. But let's go back to, I don't know, my drawing pin or my tossing a coin. I could actually get my computer with a little bit of code to simulate the dropping of that pin or to simulate the dropping of a coin or in fact anything I wanted to do. And I could let that go and do 10, 100, 1,000, a million different experiments and draw it on a graph and actually see it doing, this and getting closer and closer and closer to the actual probability to the point that, ultimately the deviations are going to be so insignificant, you're not going to really notice them. All right, so simulation can be really, really useful. Thankfully, for the moment, we don't have to worry about that. Now, the last part of this video is actually finding probabilities from areas. And again, for those of you who are sort of already ahead of the game, if you want to try and find a probability, you're basically going to do the area that's successful divided by the total area. So in this situation, we've got a dartboard. It's a red square, as you can see in the middle. Yep. And what do we got? We've got a white square of side length 12. Lovely. If a dart is thrown at the board with an equal chance of landing anywhere on the board, and that's quite important, it's got to be an equal chance, what is the probability it lands in the red area? Now again, ignore the possibility it might land on the line or miss the board altogether. Right, so there we go. So what's the probability? So we're trying to find the probability of it being red. It's going to be the area of the red divided by my total area. Because area of red is going to be my success. Well, can we find the area of the red? And again, weirdly, and I've been talking about this today with kids in my own mathematics group, if I look at this one here, lots of people will turn around and go, oh, I don't know the dimensions. And they'll see this 2 centimeters and they'll see that 12 centimeters and they'll go, oh, it's 10 by 10. No, it isn't, because this here is also 2 centimeters. If that is 12, and we know it's 12 because it says it's a square, then I've got to subtract 2 and another 2 to give me that actually this there is 8 and that there is 8. And I know that's really hard to see on this screen, but now I've got a nice way of finding the area is going to be 64 on the total area of 144. Let's fire up my calculator. He says, hoping that's going to come up. Yes, it does. Let's click on here and let's do 64 divided by 144. He says type in 100, which gives me 0.44444. So we're going to say either 0.44 with a dot on the top recurring, or 44.4 reoccurring percent, depending on what the question is asking for. And there we go, believe it or not, there we go, probabilities from area. Nothing majorly complicated from any of this. And as I said, it was going to be a short video, and there it is. So, did I successfully fulfill my learning objectives? Did I understand what a subjective probability is? Yes. How do they know it's 50%? Understand how we might collect probabilities from data? Never give a group of boys a thumbtack. Know what it means to be a relative frequency? Yes. Know how to find probabilities? Yes. Know what simulation is? Yes. I'm finding probabilities from areas. I think I'm done with this video. And again, there are other videos. It gets a little bit more complicated, and hopefully I will see you in those. But for now, let's call it. If you can subscribe to my YouTube channel, that will mean the absolute world to me. I've said it before, and I'm going to say it in every single video. That 10,000 subscribers today blew me out of the world. If I can get to 20,000 within the next 10 years, wow, goodness gracious, I'll be able to walk around these streets believing I'm a YouTuber. Not, all right, but there are more videos to come. Hopefully you found this useful. Leave me a comment below if you are watching this on YouTube and you found it useful, and hopefully I'll see you in another video. Until then, take care. Bye-bye.